Last video built the machinery of the continuous world, densities that we integrate for probability, and expectations that are integrals too. Now we start the catalog of distributions worth knowing by name. First, the flattest density of all, the uniform. Equal lengths, equal probabilities, and a weight for the bus computed honestly. Then the most important one, the Gaussian density, and the standardization trick that routes every question through a single tabulated curve. Finally, two payoffs, a noisy channel whose error rate is a tail probability, and the classic polar trick that proves the Gaussian is a density at all. The uniform random variable is the fair spinner of the continuum. Within its support, intervals of the same length are equally probable. Its density is a flat shelf. Two parameters a and b mark the edges of the support, and the height is 1 over b minus a, whatever makes the total area equal 1. Watch the trade-off. On an interval of length 1, the shelf has height 1. Stretch the support to length 2, and the shelf drops to 1/2. Stretch it to 4, and it drops to 1/4. Wider means shorter, with the area pinned at 1. The CDF is just as plain, 0 before A, 1 after B, and in between a straight line climbing at a constant rate. For a uniform variable, then, probability is a length ratio, the length of the piece you care about over the length of the whole support. Try it. A bus comes every 30 minutes, and David arrives at the stop at a uniformly random time, so his wait is uniform on 0 to 30 minutes. The chance he waits less than 5 minutes is the integral of 1/30th over the first 5 minutes, 5 parts out of 31/6. From the flattest density to the most famous one. The Gaussian, or normal random variable, is the default model for quantities shaped by many small independent effects, like thermal noise or measurement error. Its density is the bell curve, e to the minus x minus m squared over 2 sigma squared, scaled by 1 over root 2 pi sigma. The two parameters are motions, not mysteries. Slide m and the whole density slides with it. M is the center. Increase sigma and the density widens and flattens. Area again pinned at 1. Sigma sets the spread. The special case m equals 0, sigma equals 1 is called the standard normal. Remember it because it's about to do all the work. Here's the catch. The CDF of a Gaussian is an integral with no closed form. No amount of calculus produces an antiderivative for the density. The rescue is a change of variables. Substitute v equals u minus m over sigma, and every Gaussian CDF collapses to f of x equals phi of x minus m over sigma, where phi is the CDF of the standard normal, one tabulated curve computed once, serving every m and every sigma there is. The same information wears other names. Statisticians use the error function ERF, and engineers use the tail q of x, which is simply 1 minus phi of x. Different fields, same curve. Let the tail earn its keep. A binary message crosses a noisy wire. The input x is +1 or -1 with equal probability, and the output is y equals x plus z, where z is Gaussian noise with mean 0 and spread sigma. The receiver does the natural thing. It decides by the sign of y. Positive means a +1 was sent, negative means a -1. When does it fail? In two ways. A +1 was sent and the noise dragged y below 0, or a -1 was sent and the noise pushed y above 0. Picture the two densities, one centered at +1, one at -1, with the threshold at 0. Given a +1, an error means the noise beats the signal, z below -1, and by symmetry of the density that is the tail probability q of 1 over sigma. The other error is its mirror image, the same tail reflected across the threshold. The total probability theorem averages the two conditional errors, a half of each, and symmetry makes the average trivial. The probability of error is exactly q of 1 over sigma. Noise level in, error rate out, reliability read off a tail. One debt remains. Is the Gaussian even a density? Its area must be 1, yet the function refuses to be integrated directly. The classic trick is easy to follow and hard to discover. Call the integral I and study I squared instead. Squaring turns one integral into 2, and two integrals into a double integral over the whole plane of e to the minus u squared plus v squared over 2. Now look at that surface from above. Its level sets are perfect circles, begging for polar coordinates. The angle contributes a factor of 2 pi, and the radial integrand becomes r times e to the minus r squared over 2. That extra r is exactly the derivative the exponential was missing. The radial integral evaluates in one line, and I squared equals 1. Since I is non-negative, The area under the curve is exactly 1. The same normalization identity exploited once more delivers the moments. The mean is m, and the variance is sigma squared, so the parameters mean what we said they mean. The key idea of this video: the uniform makes probability a length ratio, and the Gaussian routes every question through one curve, phi.